We now move on to data visualization. Visualization is the presentation of data in a pictorial or graphical format for the purpose of increasing understanding and for gaining insights into the data. There are multiple data visualization techniques that we'll discuss, and they are shown over here. And then we will go over a section on how to select among these different visualization types and techniques. Let's start with the most basic technique, which is a histogram. A histogram presents a distribution of numerical data by using the height of the column to represent absolute frequency. A histogram shows us where most of the data lies. So for example, let's say we are evaluating 200 stocks and we are interested in knowing what are the prices of these stocks. Say the stock prices range between 46 and 65. What we might do is create 4 different groups or categories, and then we can say that in this first group, which is 46 to 51, we have 20 stocks. In the next, which is 51 to 56, we have 60 stocks, and so on. The graphical representation of this data is a histogram. We've talked about this data before. Now we are depicting it graphically, and the graphical depiction is a histogram. So notice we have 46 to 51, and then this height represents the number of stocks. The height is 20. Then in the next box, which is the 51 to 56 range, we have 60 stocks. Therefore, the height is 60. So this is a histogram. A related graphic is a frequency polygon. Here we simply take the midpoints of each bar and connect them. So that's what we do. If we look at this picture over here, essentially we are saying that for the first range we are at 20, which is this midpoint. Then for 51 to 56 we should be at 60. That is over here. 56 to 61 we should be at over here. And then the final bar, which is at 20, that is over here. So this is a frequency polygon. We simply plot the midpoints of each interval on the x-axis and the absolute frequency of that interval on the y-axis. So this is the absolute frequency, and then we have the midpoints. Next, we have the cumulative frequency distribution. Here we plot the cumulative frequency against the upper interval limits. So what does this mean? If we look at this table and we come up with the cumulative numbers, the cumulative number is 20. Then for the next one, it is 80. Then we have 180 and 200. So these are the cumulative numbers. What we now do is take each range. So this is the first range. For the first range, we will be up to 20. Then we add 60. So that gives us 80. So now over here, when we go to the next box, we should be at 80. So over here, we will be at 80. Then for the next box, we should be at 180. So that's what we see over here. So this brings us to 180. And then the final one will take us all the way up to 200. So this point over here shows us the total count to this point. So when we get up to 61, we should have 180 stocks covered. And that's why this is called cumulative. What I've shown here is a cumulative frequency distribution because we have the absolute numbers over here. If we work in terms of percentages, so this would become 10%, the next one would become 40% because these numbers are out of 200. So if we plot 10%, 40%, and so on the y-axis, then that would be called the cumulative relative frequency. So if we have absolute numbers, that's called cumulative frequency. If we use the relative numbers or the percentage numbers, then that's called the cumulative relative frequency. It's important to be able to interpret the slope of a cumulative frequency distribution. Notice that the slope is high over here. This is because in this range, a large number of stocks have been added. So when we look at the 56 to 61, this is a big increase relative to the previous box, which had 60. So we went from 60 and then we added 100 more. So that's why this is a relatively high slope. Whereas the next segment over here, the slope goes down because now we are only adding 20 stocks. So since a small number of stocks is added, that's why this slope is relatively low. Now, a quick practice question. I want you to do this before you look at the solution. So the question is, which of the following statements is most likely to be inaccurate? So we are looking for an inaccurate statement. A histogram is the graphical equivalent of a frequency distribution. So this is a true statement. So this is true, therefore not the correct answer. A histogram is a form of a bar chart, and we'll see later that this is in fact true. So this is also true and therefore not the correct answer. In a histogram, the height represents the relative frequency of each interval. This is not true because in a histogram, the height represents the absolute frequency of each table. So this is inaccurate, therefore it is the correct answer. So that point is made over here. Now let's talk about bar charts. A bar chart is used to plot the frequency distribution of categorical data. So histograms are generally used for numerical data, whereas bar charts are used for categorical data. Each bar represents a distinct category. So for example, if we have these 4 different categories which represent 4 sectors, and we want to know how many stocks in a portfolio are associated with each of these sectors, this bar chart helps us on that front. So what we are looking at here is the fact that we have about 100 stocks in the financial sector, we have about 250 stocks in the FMCG sector, and so on. So through this bar chart, we get a sense for how many stocks are in each sector. This is a regular bar chart. It's presented horizontally over here, but bar charts can also be presented vertically, as we will see shortly. A grouped bar chart, which is also called a clustered bar chart, can be used to show the frequency distribution of multiple categorical variables simultaneously. So for example, if within the financial sector, we know that we have these 100 stocks, but we also want to understand how many stocks are large cap, how many are mid cap, and how many are small cap. We can present that information using different colors. So what we have here is that the largest number of stocks within the financial sector are actually small cap stocks. So we have about 45 small cap stocks. Then we have just under 40 mid-cap stocks, and we have 20 large-cap stocks. So notice that we are showing multiple variables simultaneously through a grouped bar chart. Moving on to a stacked bar chart, this is an alternative form for presenting the frequency distribution of multiple categories. So that's what we show over here. Notice that with the financial sector, we have these number of stocks, so that's under 50 that are small cap. And then for mid cap and large cap, we simply stack on top of the previous number. So overall, this shows the number of financial stocks, but then through the stacking mechanism, we can show how many are small cap, how many are mid cap, and how many are large cap. Over here, I'm highlighting the fact that we can also present data vertically. So this is our grouped information. We can present it vertically. So within the real estate sector, we can use this presentation to say how many large cap, how many mid cap, and how many small cap stocks we have. This is the stacked presentation, and it is actually more common to present stacked charts vertically. Normally, the height is proportional to the value it depicts. So for example, over here, normally what this would mean is that FMCG is twice as much as information technology. So in our context, we have twice as many FMCG stocks as information technology stocks. So this is the regular presentation. But sometimes what we might see is a y-axis that is truncated. When the y-axis is truncated, then we need to be careful, because what happens is that below this cut, we might have a certain number. So we might have 100 over here. And then over here, we might start at, let's say, 300. So we might start at 300 and go to 400. Now, if we have two columns, one which looks like this and the other that looks like this. So this seems to be about twice as high as this. But the fact that we have a truncated y-axis means that we need to carefully look at the numbers on the y-axis. So we need to look at the 100 and the 400, and then we can conclude that this is 4 times more than this. So the point is that we should look at whether the y-axis is continuous and linear or whether it is truncated. A tree map can be used to display categorical data. A tree map consists of a set of colored rectangles to represent distinct groups. So here, for example, red represents FMCG, blue represents the financial sector, green represents information technology, and purple represents real estate. The area of each rectangle is proportional to the value of the corresponding group. So clearly here, FMCG is the largest rectangle, and this means that we have the largest number of stocks in the FMCG sector. Additional dimensions of categorical data can be displayed by nested rectangles. So notice within FMCG, we have these nested rectangles, and through these nested rectangles, we can see how many small cap stocks, how many mid cap, and how many large cap stocks we have. So with FMCG, clearly the largest group is small cap stocks, followed by mid cap, followed by large cap. Next, we have word clouds. A word cloud is a visual device for representing textual data. So the key point is, when we are analyzing textual data, we can use word clouds. There are several examples of textual data. We might, for example, be evaluating analyst reports related to a particular stock. We might be evaluating the meeting minutes from the Fed's annual meeting where they are deciding on interest rates. So there are several kinds of text documents that can be evaluated, and a word cloud is a convenient technique for doing this. When we have a word cloud, the most important variable is the size of each distinct word. The size of the word is proportional to the frequency with which it appears in the given text. So in this word cloud, financial report appears more often than any other phrase. So that's why this has the largest font. So words like finance, for example, do appear, but they come relatively infrequently. Color can be used to add another dimension. So an example of this is that we might want to evaluate a word cloud which is based on an analyst report related to a particular company, and we want to look for words that give a positive sentiment. So words like growth, words like profit, and we also want to identify words that give a negative sentiment. So words like pessimism, words or phrases like slow down. In this case, what we can do is use a color like green for words that express a positive sentiment. We can use red for words that express a negative sentiment. And then we can use a color like blue, for example, to express words which have a neutral sentiment. So both font size and font color can be used to communicate the information that is contained within a given text document. Moving on to line charts. A line chart is a type of graph used to visualize ordered observations. This technique is often used to display the change of data series over time. So for example, between 2006 and 2009, we want to look at the S&P 500 index. So this is time series data, and this line graph shows us that at the start of 2006, the S&P was at about 1300. It slowly went up, and here during the financial crisis of 2008, the S&P index came down substantially. At the same time, we might be interested in unemployment or underemployment numbers. and notice that underemployment was fairly stable till the end of 2007, but then underemployment shot up as the financial crisis hit. And that's the point made here, that we can plot more than one set of data points, which helps in making comparisons. A bubble line chart is a special type of line chart that uses varying sized bubbles as data points to represent an additional dimension of data. So here we are looking at revenue on the y-axis and then different time periods on the x-axis. So this line over here represents revenue. Let's say for a given company, the revenue went up from Q1 to Q2 in year one, and then the revenue came down. Now, in addition to looking at revenue, we might also be interested in earnings per share. So this circle over here represents the earnings per share. The larger the circle, the larger the earnings. And we are also using colors. So we can say that green represents profits or positive earnings per share, and then red represents losses. So this big red circle represents a relatively high loss of minus 5.6. Moving on to scatter plots. A scatter plot helps visualize the joint variation in two numerical variables. It is constructed by drawing dots to indicate the values of the two variables plotted against the corresponding axes. So for example, let's say we want to compare the S&P 500 returns with returns on an index that represents the technology sector. Now, what we might do here is look at the last 30 months of data. So let's say our data is divided into 30 months. 30 months ago, let's call that month 1, we might have a given S&P 500 return and a given return for the technology index. So that would represent one data point. Then this might be month 2, where we had a certain S&P 500 return and a certain technology index return. Notice that for 30 months, we will have 30 pairwise observations, where each observation represents the S&P 500 return in that month and the technology sector return in that month. The dots are drawn to indicate the values of the two variables at different points in time. So in my example, the different points in time represent the last 30 months. So we might come up with a scatter plot that looks at something like this. The scatter plot reveals a lot of information. One obvious information is the sign of the association. So we are looking at the relationship between, or the association between, these two variables. In my example, the x-axis variable is the S&P 500 return. The y-axis variable is the technology index return. Here we clearly have a positive association in the sense that when the x variable goes up, the y variable is also going up. We also get a sense for the degree of association. What we see here is a pretty strong positive association, so the degree of association is high. If we look at this example, let's say that this is variable x versus variable y. Now here, the sign of the association is negative because as x increases, y decreases. So this is a negative association. The degree of association is not as strong as what we have with the first graph over here. We can also look at whether the association is linear or non-linear. So here, clearly the association is linear. Even here, while the association is not very strong, but it looks roughly linear. In this example, we have an association which is quite strong, but this association is clearly non-linear. A scatter plot also gives us a sense for the maximum and minimum values. So that is pretty obvious over here. So we see that we have a certain minimum value here for both x and y, and this gives us the maximum value for both x and y. We can also see if there are any outliers or extreme values. In this graph, we don't really have any major outliers, but let's say we had a data point over here. this would represent an outlier, and we could then explore why we have this outlier. It could be a data entry issue, or we might actually have had something unusual because of which this outlier exists. So what we've said about scatter plots so far is in the context of two variables, an X variable and a Y variable. So here we have the S&P 500 versus information technology. We see that there is a fairly strong positive association between these two variables, and this is also mostly a linear relationship. But what if we want to evaluate relationships between multiple pairs of variables? In that case, we use what is called a scatter plot matrix. So we want to look at the association between the S&P and different sectors such as IT, utilities, financials, and so on. At the same time, we want to look at the association between sectors. So we want the association between IT and utilities, IT and financials. So the way we do that is through a scatter plot matrix. This picture over here is S&P 500 versus S&P 500. So this is a regular histogram. But then here we have S&P 500 versus information technology, and we see a positive association. Then we have S&P 500 versus utilities. Here we don't really seem to have much of a correlation. So these two variables seem to be unrelated. We can have a situation where S&P is quite high, but utilities then could be high or fairly low. Then we have S&P versus financials. This also appears to be a positive correlation. Here we have information technology versus utilities. So it doesn't seem like we have much of a relationship between these two variables. So the larger point is that we put this data together in the form of a matrix. Each individual picture still covers only two variables, but collectively through this matrix, we can look at the relationship between multiple variables. And this phrase is something you can remember because it might show up on your exam question. A scatter plot matrix makes it easy to inspect all pairwise relationships in one combined visual. Next, we have heat maps. A heat map organizes and summarizes data in a tabular format and represents it using a color spectrum. Going back to the example that we've used throughout this segment, let's say we are looking at the number of stocks in a portfolio categorized by sector and market capitalization. So we've been talking about these four sectors, and then market capitalization could be small, mid, or large. And effectively, we are saying that we have this many total stocks in the financial sector, and the split is 44 small cap, 38 mid cap, and so on. But what's different about a heat map is that a color code is being used to indicate where we have a higher number and where we have a lower number. So this dark orange number is indicating a high number of 130. Then the light orange indicates numbers that are lower than that. As we come close to our lowest number, which is 10, we move towards blue. So dark blue represents the smallest numbers, and then gray represents numbers in between. What we could do here is also have a graph which shows that, a blue color over here would be less than a certain number, and up here we would have red, which would be, our highest range. So anyway, with a heat map, we are also using color to indicate the size of each box. There are multiple uses. One is to display frequency distributions. So when we look at red, we know automatically that the number is bigger over here. And we can also visualize the degree of correlation among different variables. So if we have two columns like this, where the colors are similar, that would imply that the degree of correlation is high. And this concept would also apply across rows. So if we have two rows where the colors are very different, that would imply a relatively low correlation. But anyway, the main point to remember is that through a heat map, we can quickly display frequency distributions. Let's now talk about selecting among different visualization types. And from a testability perspective, this is extremely important. When we talk about an appropriate visualization technique, the choice here depends on why we are visualizing data. Are we trying to explore or present relationships or associations? Are we trying to understand the distribution of data, or are we making comparisons? Let's start with exploring or presenting relationships. Relationships can also be called associations. Now let's take a particular example here. Say we are coming up with a model to predict stock market returns, and let's say that stock market returns are depicted by index returns. We believe that variable X1 predicts stock market returns, and similarly we also think that variables X2 and X3 have an association with stock market returns. To evaluate this relationship, we can create a scatter plot. So we can, for example, have X1 on the x-axis and stock market returns over here. And by looking at a scatter plot, we can try and estimate or understand whether there is indeed a relationship. So basically, a scatter plot can be used to understand the relationship or association between two variables. Now, let's say we want to get to the next level and we want to see all these relationships, the relationship between X1 and S, X2 and S, X3 and S, and then we also want to see the relationship between X1 and X2, and then X1 and X3, and so on. In this case, we would use a scatter plot matrix. And we've discussed this earlier. So the key point is when we want to explore relationships or associations, if only two variables are involved, then we use a scatter plot. If more than two variables are involved, then we use a scatter plot matrix. Another technique for understanding relationships is a heat map. And I've shown you a heat map before. With a heat map, we will look at variables that have similar colors. So if we look at this top row and this third row, when we see similar colors, that would mean that the association is relatively high. So basically for this first item, we have scatter plots, a scatter plot matrix, and a heat map. So these are the types of techniques that make sense for the first category. Next, let's say we want to explore distributions. And here we will look at different kinds of distributions. Let's say we are evaluating numerical data. With numerical data, it would make sense to use histograms, and related to the histogram is a frequency polygon. And the third type of picture that we might use is a cumulative frequency distribution. And this is fairly easy to understand. What if we have categorical data? With categorical data, we can use a bar chart. And remember, the basic difference between a bar chart and a histogram is that a histogram is typically used for numerical data, whereas a bar chart is used for categorical data. Similarly, with categorical data, we can use a heat map, which we discussed earlier, and we can also use a tree map. So this is a tree map where we look at different categories based on the sizes of the rectangles. And then within each rectangle, we can have these nested rectangles which depict smaller segments within a particular sector. This is something we've discussed earlier. And as I said before, a heat map can also be used to look at categorical data. So with categorical data, the basic tools are bar chart, a tree map, and a heat map. What if we have unstructured data? So for example, we are evaluating the text associated with a speech made by the governor of the Fed, and we want to evaluate the words that were used. We want to see which words are used more often, and perhaps we also want to see how many words are used that express a positive sentiment about the economy, and how many words or which words are expressing a negative sentiment. In this case, the most appropriate tool would be a word cloud. Now, the third category is where we want to look at data to make comparisons. If we want to make comparisons, we need to think about whether the comparisons are among categories. So this would basically be cross-sectional data where we are comparing across different categories, or over time, which would mean that we are using time series data. For categorical data, where we are comparing across different categories, a bar chart would make sense, because here what we could basically do is, let's say in a given period, we want to compare the earnings per share of different companies. So if we are looking at 3 different companies, we could look at the earnings per share of company A, B, C in a given year. Then again, in the next year, we can look at earnings per share of the 3 companies and so on. So notice that a bar chart can be used to compare categorical data. Similarly, a tree map and a heat map can be used to make comparisons. If we are looking at data over time or time series data, then one strategy is to use a line chart. So for example, we might be looking at the S&P index over time between, let's say, 2006 and 2010. So that might look something like this. At the same time, we might also want to look at unemployment numbers. So a line chart allows us to evaluate variables and even compare variables over time. Another technique is a bubble line chart. So this allows us to look at 3 variables. We might, for example, look at the revenue of a given company over time. So the x-axis might represent year 1, quarter 1, year 1, quarter 2, and so on. And the line here would represent the revenue. And then at each point, we might also want to show the earnings per share. We can say that the size of the circle represents the earnings per share. So the larger the earnings per share, the larger the circle. And then we can use a color to represent whether there was a profit or loss. We can represent a profit using green circles, and we could represent a loss using red circles. So basically, with a bubble line chart, we are able to express 3 different variables and how they are changing over time. Let's conclude this segment by talking about some common pitfalls. One pitfall is to use an improper chart type. So for example, we are interested in finding the relationship or the association between 2 variables x and y. In this case, the best technique is to use a scatter plot. But instead, if we use a line graph, then obviously this will not help us with identifying the association very well. Another pitfall has to do with using selectively plotted data. So let's say that we are looking at a time series presentation of a certain variable y over time, and the variable goes something like this. So generally the trend is up, but there is this period over here where the variable comes down. If we selectively only plot this data, then it will look that y is trending down, which actually is not true. This is just noise. Overall, the trend is upwards. The third item has to do with using a truncated graph where the y-axis does not start at 0. So if you have a situation like this where the y-axis is truncated, and then let's say we have 100 over here and 110 and then 120 and so on. Now, if we have a comparison of 2 variables and our comparison looks like this, it appears that this height is twice as much as this. So let's say this variable y appears to be 2 times bigger than x. But that would be misleading because we have a truncated y-axis. The point here is that we need to carefully look at whether the axis is truncated or not, and also look at the numbers, especially when we have a truncated y-axis. The fourth pitfall has to do with improper scaling of axes. Now here, the situation might be that our variable is generally between 100 and 200, but our y-axis, let's say, goes all the way up to 1000. So now, if we plot, let's say, this x variable, then it will look very flat. And this is because the y-axis has not been scaled very well. All the data is here between 100 and 200, but we have created a y-axis that goes all the way up to 1000. So these are some common pitfalls associated with the different visualization techniques that we've discussed.